See it one more time. Thank you for the push-ups, Tyrion. There we go. And Lorenz Force in action. So, we are going to talk about the Lorenz Force today. First, let me write down the Lorenz Force Law. So again, we're going to kind of keep this a little bit on the introductory physics side today. But we're still going to see some cool physics. So stick around. We're going to actually do... I guess maybe I should paraphrase that. We're going to start with introductory physics, and then we're going to slowly move into more complicated concepts as we go through it. But this isn't going to be a very long lesson. It's only going to be about 10 minutes. So stick with me, and we'll get through this. So the Lorenz Force Law. The force is equal to the charge, some we're building, yep. We're doing Lorenz Force Law build. Well, it's more like demonstrations with a small build. We might build something at the end, depending on time and everything like that. But yeah, you'll see. You'll see. Magnetohydrodynamics is the name of the game today. So we take some charge, multiply it by the electric field plus the velocity of the charge crossed with the magnetic field. So let's talk about this equation and what it means. So you might know the force equation as this, Q times E, where we have the some charge Q multiplied by the electric field. And this describes a force on a charged particle in an E field. This is the first half of the Lorenz Force Law. When you just multiply Q by E, F equals this. That's what we talk about when we just talk about a charge in an E field, right? But then there's the other part of it, which is QV cross B. And that's the one that we're going to be playing with a lot more today. QV cross B. And this is going to be, it describes the force on a charge in a magnetic field. So, not as a tensor, it's a vector. Not my problem. I'm not laughing because it was funny. Oh no. So another way you might have seen this is the current times some displacement vector crossed with the magnetic field B. Again, it's just a way of rewriting this. This is easily seen how it goes from one to the other. If no one's ever seen this, if no one ever showed you this, it's a very simple, like a two-step thing. And the way I like to think of it is the current is equal to the change in charge over the change in time. The velocity is equal to the change in distance over the change in time. So it's pretty easy to see that you can kind of rewrite these. If these are the same system, then we're going to evaluate over the average time. And we can find out that we'll have dq dq over ds is equal to, how do we do this? Let's see. Is equal to I over V. I think that sounds right. And then this is just a charge density. Okay? This is just a charge density, which means this is also equal to the charge over the length. So then we could just rearrange this QV equals IL. Dunzo. That's just how I like to do it. How I show my intro physics students when they are curious why this and this are the same thing. Okay? Just a little side calculation there. Now we can talk about the force and the direction of the force via right-hand rule. And there's really two right-hand rules, so we're going to talk about both right-hand rules, okay? So take your right hand, okay? And now there's two right-hand rules. We'll start with the one right-hand rule, where you're just talking about the direction of a magnetic field around a wire of current, okay? So that is, your thumb always goes in the direction of the current or of the motion, we should say, because we're talking about the motion as positive. The current, by convention, goes from plus to minus, so it's going with the positives, yeah. Not with the electrons, which seems a little bit strange. But anyway, so you take your thumb, you put it in the direction of the current, and then your fingers make the magnetic field that wraps around the wire, okay? So there's two things to remember with the right-hand rule. Your thumb always goes in the motion of the current or the motion of the particle, the charge, the positive charge, and your fingers always go in the direction of the magnetic field, okay? So for the one right-hand rule, for the direction of a magnetic field around a wire, take your thumb, put it in the direction of the current. Your fingers wrapping around make the direction of the magnetic field. Here's the other right-hand rule, the one for Lorenz Force Law, okay? Your thumb, if we're doing this one, let's do this one right here first. Your thumb, direction of motion, so it's the direction of the charged particle. And your fingers go in the direction of the magnetic field. So those two things remain the same. Thumb goes in the direction of the motion of the charged particle. And your fingers go in the direction of the magnetic field. And the force is the palm of your hand. So for instance, if we have a charged particle going this way, a magnetic field going up, the force is this way. Okay? If we have a charged particle still going this way, but now the magnetic field's going down, our force is this way. Okay? So those are the way we do the right-handed rules. But I'm left-handed. Hey, Lobo, good to see you. Use the other left hand. There we go. I don't like the middle finger one. I don't use that one. Like this one, I don't do that one. Nope. Nope, nope, nope. Because this way is simple. Fingers always go in the way of the magnetic field. Thumb always goes in the way of the motion. So for example, let's do this one. Okay? Now we have thumb goes in the direction of the current. So let's do it this way now. So the thumb goes in the direction of the current, so say the current is going this way. Fingers in the way of the magnetic field, so the magnetic field's up. Force, this way. Okay? That's how, so that's the right-hand rule. So for instance, if you have some capacitor with rails that go like this, and there's a magnetic field coming out of the chalkboard, and there's a wire going this way, a bar going this way. And we put a current, say I, and it's going clockwise, counterclockwise, wow. Counterclockwise through the loop. We can figure out what direction this bar is going to travel, right? So if the electric field is coming out and the electric field is coming out, the current is going this way, so the force is going to be coming down. So we can figure out that the force is going to push the bar this way. Now there's some things you can say about this, like if the bar is sliding, then this magnetic field inside this area is going to get larger, which means there's going to be an induced current that goes the opposite direction. But what will end up happening is you will only end up slowing down the acceleration, but you won't end up slowing down the velocity. So as the bar is coming down the magnetic field coming through is going to be greater, which means there's going to be an induced current going the other way, but it's only going to reduce the acceleration. It will not be reducing the velocity. So you will eventually reach some terminal velocity, but yes, and that's how certain railguns work, which we'll see in a little bit. Anyways, but what are we going to be doing today? We're going to be talking about hydromagnetic dynamics, magnetohydrodynamics, or whatever the arrangement is. Yeah, but how are we going to talk about magnetohydrodynamics? Well, consider the periodic table. Okay? well, actually, before we go into the periodic table, let's talk about energy levels and electrons and how they work, right? And this may look like chemistry. But wait, this is all describable and is the subject material for condensed matter physics. So don't be fooled by the rocks that I got. It's still physics, I swear. Okay? So let's talk about water, H2O. Something like that. Some sort of chemistry nonsense, right? But like, if we were to talk about the molecule, it's going to be one oxygen with two hydrogen. And we could write out what the hydrogen orbitals look like and the oxygen orbitals look like, which we're going to do in a second. And really what we're going to end up seeing is that hydrogen consists of one s1, meaning that there's one electron in the outside orbit. Now, the amount of energy... no, it's not what it looks like, I swear. Isn't all, all chemistry just one page of quantum mechanics? I don't know about that. But we're going to be talking, I was tempted to write down some Hamiltonians, but I thought, maybe that's a little bit too much mathematics. So we're gonna pause the Hamiltonians, and if you would like to see it, then maybe we'll do it at the end or on Wednesday or something. But you can describe the amount of, so if we had two energy spots right here, and this is the 1s orbital, there's one electron, and this one's empty, okay? Now, oxygen has 1s2, oops, I don't know why I put that up there. I don't know where to put it, so we'll just put it anywhere. Physicists don't have to follow convention, so we can just write wherever we want. 2s2, and then 2p4, which means that its final energy level, P, there's supposed to be 6. So its final energy level looks like this with 4 electrons. There's 6 spaces. 4 of them have electrons in it, okay? But luckily, there's 2 hydrogen for every 1 oxygen. Oxygens love to take electrons. They'll take them from, like if you have, we talked in my advanced condensed matter class about cuprates, which are like copper elements with, or alloys or whatever you call them. Who cares, right? Some mixture of elements with copper in them. And anything that has oxygen, and oxygen loves to take electrons. So, oxygen's going to take the 2 electrons from these 2 hydrogens. Each hydrogen has 1 extra electron, so oxygen's going to grab it. And then it's going to make the oxygen 2 minus, right? And H plus. You're going to have 2. Maybe I should rewrite this like this. Something like that, where you'll have 2 positive H ions and 1 negative 2 charged oxygen, right? Now, this is all well and good. Once you fill up these energy levels, this molecule is happy, okay? It's comfortable, and it's going to do its thing. But like, so we can talk about these electrons. So really what it is electrons hopping from hydrogens to oxygens and just hopping around. And we can write about that, and we can write that down in Hamiltonians because it's all about the energy of that interaction, the energy of an electron moving around. Now, what does that mean? So we know that water can naturally have some ions in it. There's going to be some other things floating around. Hydrogen has a really strong tendency to strip electrons from things. That's why it's one of the things that dissolves molecules really well. It'll pull things apart really nicely. So usually in like tap water and stuff, there's a lot of free ions. So what does that mean? What does that mean in terms of Lorenz Force Law? Well, that means that if we take an arrangement and set it up where we have this setup, but instead of setting a bar across, if we just charge up 2 rails and then put a magnet under it, then the free ions from in here will act as electron hops, where electrons can hop from ion to ion and complete the circuit around here. And then there's a force that pushes down here. And what does it push? It pushes water. But yeah, so that's what we're going to be working on today. We're going to show some cool effects of how this works. And then what we're going to do is we're going to add salt to it. Table salt, NaCl. NaCl, this is a project I'm working on for that class. NaCl is, let's see, so Na is, oh geez. We can talk about it. I guess I got to go to the periodic table. That's not the periodic table. So where's Na? Na is right here, sodium. That has, what's that, 3s1. And Cl has 3s2, 3p5. So that's going to try to take that 3s1 from Na. So let's go back to the board really quickly. So what does that look like? Well, that means that Na is going to have a bunch of closed orbitals, like all of these that are closed, and then it's just going to have 3s1, and then Cl is going to have a bunch of closed orbitals. It's going to have 3s2, 3p5, and then it's just going to take this last one down there. So you'll get this nice thing where it takes an electron, now it's minus and the sodium is plus, and we have more ions. Well, like I said, water likes to take them. It likes to take electrons, so it's going to break these apart. And what's going to happen is we're going to have extra ions floating around in the water. And as we introduce charge to it, then the charges are going to be hopping around from ion to ion as they make their way through from one side to the other side. And it's going to be a much stronger force. That's what we're going to hopefully see. These forces are small. These forces are very, very small. So, right. Bear with me when we're doing them. They're very, very small forces macroscopically. So then what's going to happen is as these molecules, as these ions start floating towards these plates, which have lots of charge on them because they're conductors, what's going to happen is they're going to react. Because they're ions, they're looking for electrons. So what we're going to see here are chlorines acting, or chlorines on one side where we have chlorine, and then the other side is going to be the sodium, and it's going to look, both sides are going to be relatively violent, but it's just going to be a lot of bubbles, which does interfere a little with the thing, but you'll see. NaCl plus H2O, I think it's 2 NaCl plus 2 H2O yields Cl2 plus H2 plus NaOH. And if you were just to take sodium and put it in H2O, you get this stuff, which is where the violent reaction occurs. So one side is going to be chlorine gas happening, and the other side is going to be the sodium and the water making a different chemical compound. But it's going to be interesting. So what we're going to do now is move over to our building space. I have some demonstrations to show. We're going to see how these things work a little bit. You're going to have to give me just a second while I get it set up. Okay, so let's see Lorenz Force Law in action. So we're going to start by taking a couple magnets that are managing to hold on to everything. And we're going to put them underneath this set of rails, this set of aluminum rails, just like that, okay? Now, like we talked about before, like we talked about before, if I add some current to this wire, or to this, these rails, I should say, if we can complete the circuit, since there's a magnetic field underneath, then we should see some, ooh, geez, I gotta be careful about that. We should see some motion out of our object. Now there's a current running through this contraption here. And if you'll notice that lead, pencil lead, is not magnetic. Graphite is not magnetic. CERN called, they want their magnets back. So if you see here, as I rub this this lead against this doesn't keep it, right? This is not magnetic. It wants nothing to do with it. So, So it's not magnetic, but it is conductive, right? So there's some current going through it. So what happens if I set it down? Okay. Okay, it just goes to a side. I'm not pushing it or doing anything like that. I'm just literally setting it down, and it starts taking off. And then I could even try to push it back against it. Let me see here if I can do this. Ah! Stop that. It just doesn't want. Stop it. But like, this is Lorenz Force Law in action, right? Like, you can see that all I'm doing is just releasing it. It has to be over the magnet. There it goes. Is the aluminum connected? No, the aluminum's not connected. Check it out. Here's the bottom. The aluminum is not connected at all. It only connects once the graphite is on it. And then the current goes through it. Ah, jeez. But yeah, so that's the Lorenz force. Let's see it one more time in detail. If I drop it, so we have a current connected. Here's the magnet. If I drop this right in the middle, it's going to be a... I'm sorry. Oh, geez. If I drop it right in the middle, there we go. It's going to experience a Lorenz force. Whee! And then if you were to switch leads, so now if you change the way that the leads are, put it down, it will go the opposite direction. Okay, just as we anticipated. Just as you anticipate when you do the right-hand rule, if you change the direction of the current, the force will change direction as well. That is how we talk about the Lorenz Force Law. And we just saw it in action, and that's really cool. So now we saw it in regards to, some pieces of aluminum and how that might work. But now what we really need to do is talk about this hydrodynamic one. Now, we have some current going through these rails, and if we put in, hold on, let's see if we can go to this camera right here. Now, if we put in some food coloring, we should expect, and I will pull the camera up to take a closer look once I get it rolling here. But let's put it in the center. And there's not going to be a lot of ions in this. So there's going to be some denseness from the water, or from the food coloring, that's going to make it kind of difficult to move along. Let's see if we can get some motion here. There you go. Do you see it? Do you see it moving? Now it's moving very, very slowly. But that's the force that we're dealing with right now. There's the Lorenz force is actually causing the water to move via that interaction that we talked about, that Lorenz force, where the oxygen, the natural ions that are in water are causing the current to continue, and it's spreading out to the end of, then that means that the current is going through those ions, and there's a small net force to the left. And now what we'll do is we'll empty this out, and we'll do some salt in the water, some table salt. Sorry, I can't find red. I don't know where red is. Maybe we'll do both. Anyways, so once we connect it now, I managed to do this without this getting all screwed up. All right, there we go. There we go, now we're getting some good reaction. Oh yeah, look at it go. Here we go, ready? See that motion? Look at all of it just get pushed out. Like crazy get pushed out. See, that's a lot faster now. Now this ball here is really dense. But watch here, let's see if we can't make something happen here. Look at it all just get dragged to the side there. That's the Lorenz force I was talking about. See how see all of those, so these are all charged ions just getting shoved, and those electrons are hopping from ion to ion, you know, going through the circuit and completing it. And then what's happening is causing a net force on the rest of the water, a force in this case to the left. Yes, there we are. Lorenz Force Law, it works. A few shorted wires later. But it does work, and it's just cool because like you can see it in action. Let's see it one more time. Thank you for the push-ups, Tyrion. There we go. And Lorenz force in action. Look at it get sucked all the way down there. Now this is cool. This is what I was hoping for to happen right at the beginning of today's building stream. But yeah, so it's exciting to see how this works, and like this is cool. Obviously, like we have a lot of batteries here, and you can see it kind of like get poured out the other end. But like, and you can see all of the exothermal reaction, and it's a lot more force than the other when we didn't have the salt. But again, the problem that we have here, the reason why this doesn't actually work in like practice, is like, see all these bubbles and everything? That's all energy loss. That's all heat loss through exothermal reactions. You have the sodium reacting with the water, and you have the chlorine ions who are grabbing their electrons and releasing themselves as chlorine gas. And this is causing, you know, a lot of energy loss in the system. So while it's kind of cool, you can imagine putting these on a little floaty thing, which was the plan to do if the first part worked well, and it would putter around at an incredibly, incredibly slow speed. You know, but the reality is that all the heat and energy lost.